So before we move forward, let's recap what we have so far. So far, we can solve heat diffusion problem. We can solve these problems. Either we have one dimension or two dimension problems. We can solve these problems. Either we are solving steady state or transient. And we can do that by implementing any type of the finite difference method, central finite difference if we need to do, forward finite difference, or its backward finite difference. So this is what we have so far. Before we leave the diffusion problem and start jumping into the fluid flow issue, I want you to think, can we do that? We did all of that in Cartesian coordinate. Correct? So we did the Cartesian coordinate for this problem. So I would like you to think how to do this kind of problem if we are solving in for a rod, cylindrical coordinate. Can we do that or not? We can do the analytical solution, but I want you to think how to implement finite difference method in cylindrical coordinate. So, for example, if I give you a solid body here, and I give you Tmax at the center of this body, then I would like to get the temperature distribution at different distance from the center line using the finite difference method. Definitely, the model that you're going to use is the heat diffusion equation. Let's start with one dimension. Heat diffusion under steady state and no heat generation. If you put these conditions here, this is a very simple heat conduction problem. So if you know what's Tmax, if you know what's T surface, and I would like to get the temperature somewhere in the middle here, like T1, T2, T3, I can do that analytically. It's well known. I can start from 1 over R, partial by partial R, KR, partial T by partial R. This is the first coordinate in the cylindrical heat diffusion equation. Then I'm going to ignore the phi and z coordinate since I'm solving one dimension problem. Q dot is going to be equal 0. I said there is no heat source in here, and steady, so the right hand side will be 0. We can do the analytical solution for this problem. I can integrate double time. I can use a boundary condition to get that solution temperature. So you can go all the way until you get T as a function of R. Then you put the value of coordinate R for each one of these nodes, and you can get the temperature. That's the first approach. That's analytical solution. The other approach that driven actually from the analytical solution is use the thermal resistance. So you could present here as Tmax. Maybe this is my T surface. Then you can present multiple thermal resistances. You guys recall that? Say this is T1, this is T2. I maybe need another resistance, that T3. Then I have, this is T surface. Then this is R. And you go and calculate the thermal resistance. It's natural log of R out over R inner divided by 2 pi KL. So you can play with the thermal resistance and you can do some calculation and get the interfaces temperature. That's still driven from the analytical solution. But what I'm asking for, how to take this equation and do discretization using central finite difference method. You guys need to think about this. Then you can validate your numerical solution using any one of these two approaches in here. So think about it and try to find a way to do that. That's quite, there's no challenge. It's straightforward. You just need to give a little bit of more time in here because all what we know that you can discretize a differential equation by removing the first derivative and the second derivative, and you put the equivalent nodal relationship to convert that differential equation into algebraic equation. So think how to rearrange that kind of equation you see up here to make it applicable for the central finite difference method. So think about it. It's really a good approach to do. Next would be actually moving to we would like to start involving the fluid flow problems into the analysis. And this is the second logic step. You move from diffusion into convection problem. So to do that, we have to put some, there's no restriction. It's just some bullets to explain the approach, how to look into a fluid flow problem. The first step that we did in the diffusion problem after we have our design is to look into the model or the governing equation. And for the previous cases, when we dealt with the diffusion problem, most of the governing equation was a heat diffusion equation with the different simplification forms. But now, what would be the governing equation if we are dealing with fluid flow? So I will put that governing equation in CFD. Again, these are the kind of equation that can describe fluid flow, and later on to describe both the heat transfer and fluid flow simultaneously at the same time. There are basic equations that we need to solve to describe a fluid flow, at least for now from the hydrodynamic perspective. And when I say hydrodynamic, I mean the velocity and the pressure. And later on, we'll look to the temperature as part of the energy equation. So we have the very famous equation that we use to analyze fluid flow problem is actually the conservation equations. I mean the mass conservation, momentum, and energy. These are the fundamental equations we use to analyze fluid flow problems. These equations, the mass conservation, momentum conservation, energy conservation, they exist in two different formats. It could be in a differential form or integral form. It could be differential or integral forms of the conservation equations. So I'm going to call that conservation equations. Okay. Sometimes people talk about, it's a little bit of confusing. Sometimes people say, okay, mass, momentum, energy, the combination of the three conservation equation, we call them Navier-Stokes equation. And some other reference, people said, no, mass and momentum only are called the Navier-Stokes equation. In some other reference, they call the momentum is Navier-Stokes equation. So let's generalize that. We said that Navier-Stokes equation is the set of equations that describe partially or fully the fluid flow problem. So Navier-Stokes equations. Again, depend on the reference you're reading. It could be only the mass plus momentum, could be only the momentum, it could be the combination of mass, momentum, and energy equation. Keep in mind that Navier-Stokes equations is describing the macroscopic flow behavior. So the Navier-Stokes equation doesn't look into the micro scale. It doesn't look to the velocity of the molecules or the momentum of molecules or the temperature of molecules. No, it describes the fluid as bulky. So it's a bulk, it's a macroscopic flow behavior. We mean that we're looking to the macroscopic property. So we're looking for the mass flow rate, bulky mass flow rate. We're looking for the momentum. We're looking to the velocity. We're looking to the temperature of a bulk fluid flow. Also keep in mind Navier-Stokes equations, the differential or the integral form, up to now, up to this moment I'm recording that video, have no exact solution. We cannot solve Navier-Stokes equation exactly, analytically. So, which means that we have to do assumptions to simplify so we can actually solve. After you do the assumption and the simplification, you can either solve analytically or numerically. And that's our CFD work. But without these assumptions and simplification, it would be impossible to solve the exact Navier-Stokes equation. Okay? The equation has been developed between the 1600s to the 1885. Started with many simplification. For example, it started with the complicated forms, then some assumption came to be consider the effect of compressibility, so rho was included. Then it's upgraded to consider the effect of viscosity, mu, and so on. And this is take from Isaac Newton, Sir Isaac Newton, when he started with using mu equal constant and upgraded to Bernoulli, Navier, Boisson-Stokes equation, and so on. So it's a historical development until we reach the final form that we have nowadays that consider all these kind of variables. So Navier-Stokes equation in the existing situation right now, the existing form, consider for compressible or incompressible, for inviscid or viscous flow. It's including all kind of resources, energy source, disturbance source, momentum source, whatever it is. So it's now in the most, I don't want to say complete, but the most mature forms to use that cover all our existing problem, at least in the level of the educational size. So that's just a little bit of introduction about the governing equation, the models. Mostly it's Navier-Stokes equation that we're going to use all the time to solve these problems. So since Navier-Stokes equation is looking to the macroscopic flow behavior, the analysis in fluid flow or fluid mechanics is actually divided into two ways, how you look to the problem. We call that actually approaches. Analysis approaches. So to make the analysis to the fluid flow problem, we have two basic approaches to consider. The first one is called the Lagrangian approach. The second one is called the Eulerian approach. I will explain what's the difference between Eulerian and Lagrangian approach when you analyze the fluid flow. So let's look into that. So let's look to the first approach, which is the Lagrangian. Let's assume that you are interested to measure specific property of fluid. So let's assume this is, you are interested to measure the velocity of fluid. So what happened is you specify a fluid particle at specific location. Let's say this is a location I'm interested in within the bulk of a fluid, and I would collect data for the velocity of that particle. So that's that velocity is becoming now a function of x, y, z, and at specific time t. Then if I'm measuring that velocity from a reference location, let's assume this is vector A here. Then and this is a fluid flow domain here, so that's the coordinate. So that's a specific location of a fluid particle. I will measure that velocity. If I want to keep observing the fluid velocity all the time, what I'm going to do, I'm going to track that specific particle as it travels along the fluid flow. So after a certain period of time, that particle will be transporting somewhere and it becomes here. Now, the velocity of the fluid by observing the motion of that particle will be a function of a new position x and new position y and new position z at advanced time. And now it seems to be that x, y, and z itself, it's becoming function of time too. So now the observation of the fluid properties can be picked up by tracking a fluid particle as it travels and considering the change in both time and position to collect the information about that fluid flow. So, so that fluid properties, I picked up velocity as an example. It could be the pressure, it could be the temperature, are obtained by tracking fluid particle. So imagine you are actually like riding that fluid particle and you are measuring that velocity at this position. And after a few seconds, you're going to be in a different position. You're going to record the new position, the time, and the new velocity. Then you're going to continue with that particle to travel with it. And after a certain period of time, you will find yourself at new position, at new time. So you travel with that particle and collect the data to observe what is the fluid property as the fluid itself is occurring. Okay, that's a Lagrangian approach to collect data and understand the fluid property like velocity, pressure, and temperature. The second one, let's make them side by side. The second one is the Eulerian. Actually, E should be capital. The Eulerian approach is different. Eulerian approach is fixing the observation to a specific position. So if that's your coordinate system, you're going to pick a location. And this is the particle has a location x. It's not the part, it's the position x, y, z. And what we're going to do, this is where I'm going to put my probe, my sensor to measure the velocity. Then what's going to happen, that position will be fixed. But you're going to keep your eyes on that location all the time to observe, say, the velocity of that location, whatever that particle going through it. So after the time goes on, you will have a fluid particle going through that location, then leave. And after a certain period of time, another particle will come in and leave. So we keep our eyes focused on that spot. And whatever is going or passing by, we will just record the data at that location. And that's the Eulerian concept. So fluid properties are obtained by observing fluid particles passing through fixed location, a given location. So x, y, z is always constant. The only variable that we're going to have here is the time. In the previous case, the Lagrangian, both everything is a function of time. X, y, z are function of time, and the time itself is a variable as well. In the Eulerian approach, we fix x, y, z, and the only variable that we have is the time. So that's how look to analyze the fluid flow problems. So again, this is recording the data of a traveling particle, changing position and time. This one is recording data for a specific location for every particle passing through that given location. So that's how we analyze the fluid flow problem. Let me give a second example to just make the idea closer to your mind. Let's assume that we have a river bank and there is a factory built on that side of the river, and this factory is actually dumping the river some of the chemicals produced into there. So what happened when the chemicals start dumped in, there will be, and the fluid flow is going that way. So all the chemicals will be driven by the stream flow down the river into that direction. So, and I'm interested to know the concentration of that chemical species into that river. So we have two approaches here. The first one, I will ride a boat and hold a sensor in my hand. Then I will allow the boat to travel with the river and get into that contaminated zone to record the data of the concentration. So how the concentration plot looks like. So when you do the concentration versus time, your sensor will read 0 all the time because I didn't get into the zone of influence. So I'm going to read 0. And suddenly, as soon as I get into there, right, as time goes on, I will have the concentration jumped up. Then it will remain maybe constant until I start approaching to go out and it's decay. So let's assume that I'm interested to get the data in here, at that location here. So the sensor will read 0 all the time here. Then the concentration will start going up. And at that time, I can mark at that location. Okay, I reached that location here at that specific time. And this is the concentration of interest. This is C, concentration of interest. This is the first approach. The second approach is, okay, no, I'm not going to do that. I'm going to stood up on the riverside here. I'm going to put my own sensor at that location of interest, and I will let the time to go on. Okay? In this case, if you are recording versus the time for the concentration, your initial reading is not going to be 0, right? You will have a specific reading. Then as time goes on, maybe you have a fixed concentration for a time. Then when the concentration, as time goes on, the factory is dumping chemicals, the concentration will increase and will continue somehow. Okay? But if you read at the same time of interest, you should get the same concentration here. So in the case number 1, this is my Lagrangian approach. Why? Because I jump over the boat, I ride my sensor over a fluid particle and start traveling with the fluid stream. The position of the sensor is functional of X, Y, and Z, and T is the position and the time. Both of them are changing at the same time until I capture whatever I want. In the second case, I fixed my sensor position, and the only variable I have is the time. And I should reach the same answer, either I'm using Lagrangian or the Eulerian approach. I hope that give you idea of the different approach that we are dealing with to analyze the fluid flow. So can we satisfy both approaches at the same time? So for example, make that apply to what we are trying to do. Let's assume that you have a specific control volume, and I'm interested to collect data about the velocity in that for the fluid flow going through that control volume. So what happened is, if I'm using the Eulerian concept, what I'm going to do, I'm going to keep my eyes open into that control volume. That's my fixed position. Then I'm going to look to the fluid particle here. As soon as it gets into here, I'm going to record the velocity of that fluid particle. When it's inside the control volume, then it will leave, right? So I will record the data at that time here. Then a second particle will come in. I will do that in red. It will flows into the control volume. As soon as it's inside the control volume, I will record the velocity before it leaves. So I'm collecting data for different particles inside that control volume. Then I say, okay, the bulk flow velocity, for example, is this. That's the Eulerian one. Can we apply Lagrangian to collect the same data? we know that Lagrangian means that you have to fly, you have to travel with the fluid particle. If I get the same control volume and I start looking to a fluid particle that entered into that control volume, then I will track that that particle as it travels only within the control volume. When it leaves, I will leave that guy by itself. So the observation now is to follow that particle, collect the velocity here, 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 but it's only within a small control volume, which means that the time interval is so small. So in this situation, both, this is the Eulerian, this is Lagrangian. So for small delta t within a control volume, both approaches meet. So we can, in this situation, Lagrangian for a selected small time interval can exactly meet the Eulerian approach. Okay, so that's just some people talk about, okay, we can actually make them meet. We can, they shouldn't give us different results if we pick up a small time interval. Okay, again, remember, Lagrangian is give you physical description of individual particles, right? So you keep your eyes observing a specific particle, right? But the Eulerian give you more the field function of a fluid within a controlled volume. So Eulerian is more macroscopic picture. Lagrangian is microscopic picture. So I will write it down this way: microscopic, but this is actually more macroscopic. I hope the approach is understood now, and we can move forward with that. So